What's up, guys? In this video, we're going to talk about entropy and explain what it is through an example of Shakespeare text. I wanted to make this video to talk to you about entropy because it is actually often a mysterious topic, even though it is relatively simple to understand. It comes up often in data science and even more generally, most areas of mathematics. Now, what I'll be talking about goes back to a 1948 paper of Shannon. This paper has been cited nearly 100,000 times according to Google Scholar, which is absolutely insane for a paper. This already ranks it amongst one of the most cited papers of all time. In this video, we're going to talk about one of the applications of this paper, in particular to the compression of text, through an example so we can see what's going on. So what exactly is entropy? To really discuss what it means, we have to know what the surprise of a random event is. Imagine we're playing the lottery and we actually win it. Then the surprise of winning the lottery should be astronomical, as our chances of winning are so small. Shannon, in his original paper, actually gave a mathematical formula that described the surprise of a random event, which is pretty cool. For those of you interested, it's actually just the log of 1 over the probability of the event. But we're not going to get into that right now. Now, entropy is actually just the expected surprise of a random event. So let's go back to our playing the lottery example. Most of the time, we're actually going to just lose and we're not going to win anything. So in this case, the expected surprise should be very small because basically all of the time we're just going to lose, and that's what we expect. Entropy is a way to quantify what this expected surprise is in terms of a mathematical formula. Now you might be wondering, why is this such an important concept? It really comes up in so many different areas of math and also data science. For instance, the concept of cross-entropy loss, which is something you might come across pretty early in your data science journey, is really derived from this notion of entropy. Moreover, some of these large language models, for instance the one that drives ChatGPT, makes use of the notion of entropy when it's training. Roughly what's going on here is that we train our models so that the expected surprise of the outputs is minimized. Alright, let's jump into an example to see a bit what's going on. So the example I chose is a portion of Shakespeare's plays. Now why would I choose this? Well, actually it goes back to a blog post of Andre Karpathy where he talked about the unreasonable effectiveness of RNNs. This blog post was pretty popular and therefore the dataset somehow became famous. So in this setup, our goal is going to be to compress the text into bits, that is a bunch of zeros and ones. One natural way to do this is to compress each character into 8 bits. Python actually has a built-in way to do this, so we can see one way to encode each character into 8 0 and 1s. For example, here I'm encoding the character lowercase a into a bunch of zeros and ones, as you can see. Now a natural question is, how small can we compress this file? It makes sense to want to compress the file as small as possible if you wanted to, say, store the file or send the file to someone else. It is important to note that the file has about 1 million characters. If we chose to do the encoding, where for each character we used 8 bits, then this would really mean that we would need about 8 million bits to encode this file. I will say that this file only contains 65 unique characters. So really it would be enough to use basically 6 bits to encode this file. However, going forward, we're going to see we can do much better than that. Now I've introduced the problem that we have to compress this file. So how many bits per character can we expect to have on average when we encode this file, if we're doing it in a clever way? It turns out that the notion of entropy basically answers this question. To see this, we're first going to look at this nice picture. This is a bar graph of all the different character frequencies. You can see some characters appear more often and other characters appear less often. So what we can do, if we're trying to be clever, is for the characters that appear more often, we can try to use less bits in the encoding. That way, because these characters appear so often and we're using less bits, on average we'll have a smaller compression. But again, how small can we expect to compress this file? So what I'm about to say is actually very surprising, maybe even mind-blowing, but actually how small we can expect to compress this file is given by a pretty simple formula called the entropy. We first compute the frequency that each character appears in the file, and then we convert these frequencies to probabilities. We then plug these probabilities into the entropy formula, and this gives us approximately 4.8. That means we can expect a good encoding to take approximately 4.8 bits per character to properly encode. In fact, there are various ways that people have figured out how to achieve this bound. Here, I chose to code up the Huffman encoding just to see what was going on. In fact, it gets pretty close to this entropy bound. Let's see how it works in practice. So here, I'm taking this famous Shakespeare quote, which actually doesn't appear in the original data. And I'm going to see how it's compressed. So here you can see that here's the string that it's compressed to, a bunch of zeros and ones. And here you can see the average number of bits it takes per character to encode. So roughly what we expected. Alright, so to conclude, in this video we saw that entropy is a way of figuring out how small we can compress a file. What's cool is that entropy is actually a relatively simple formula, but it's solving quite a challenging problem. It does turn out that entropy pops up all over the place in mathematics and data science, so it is a concept that's worth getting to know. Alright, that's it for this video. If you want the code I used, the link is in the description below. Also, if you do like the video, please subscribe, as it's good feedback for me to keep making these kind of videos. Alright, that's it for this one, and I'll see you in the next one.